Okay. So homework for today was to implement our generic binary tree that allows us to add values to it and have those values show up in the correct locations. And we're applying the binary tree rules. And then we're going to test our tree. We're going to implement the visit in order method, which should show a sorted list in the event that your tree was properly built. All right, so like we kind of looked at last time, we're going to need a binary tree object. So a binary tree has a root node. It has abilities, visit in order, visit post order, visit pre-order, but we only had to write visit in order for this. We'll write the other two today. And then a node has a payload, a left child, a right child. All right. So let's go over and write this guy. So this will be under 300. Create a new file, or I'm sorry, not a new file, a new folder. Binary tree. Inside of binary tree, we're going to create a new folder or a new file called node CPP. Actually, it'd be node HPP. We'll create the header file first. All right, inside here, we're going to have class node with private section and a public section. Private section, a node will have a payload. That's the kind of thing we're going to store inside of our node. Public section, we're going to go ahead and get the ability to get the payload. So we'll say get payload like this. We're also going to have a constructor for this guy. That'll take in a payload. All right, so we'll leave node like that for right now. Now we're going to go implement this guy. So we'll need another new file, node CPP. We will include node HPP. And then we'll go ahead and implement the node constructor. And this guy will set our payload equal to whatever payload was passed in. And then we'll write our get payload. This guy will return our payload. All right, now every node also has a left and a right child, which are nodes. So inside of our class, we're going to have a node pointer, left child, and a node pointer, right child. Inside of node CPP, when we first create this guy, we're going to set left child equal to null, is a capital that. That might be in standard lib. And right child equal to null. I'll go ahead and include standard lib, which gives us access to that null placeholder. If I hover over that, I think that's probably just a 0. No, whatever. Looks like it's a built-in thing, underscore underscore null, which is probably a 0. All right, so that's what a node will be initially. We're going to add some more abilities to this as we go. All right, now we're going to build our binary tree. HPP. We'll have our class binary tree. We'll have a private and a public section. A binary tree has a node pointer root. And in order to have access to node here, we need to import, or include rather, node HPP. Now he knows about nodes. We need to have a constructor for this guy. So we'll have a binary tree. He'll take no parameters. And then we want to have the ability to add something to the binary tree. So it'll be void add. This guy will take a payload as a parameter. All right. Now we're going to go ahead and go into our implementation file for binary tree. So new file, binary tree CPP. We will include binary tree.hpp. We're also going to go ahead and include standard lib. So in our constructor here, we'll set this root equal to null. There is no root to our tree initially. For our add function, we want to put a comment. Well, we want to attempt to add the node that has the payload in it to our binary tree, following the binary tree rules. All right, so we can add this guy to the top of our tree if the top of our tree is null. So if this root is equal to null, we could also just say if not this root. So the equivalent way of writing this would be if not this root. This says if this guy is not a thing. All right, but this is maybe the more straightforward way of writing it for us right now. So if our root is currently null, then that means that the place that this new node is going to go is right here at the top. So we'll go ahead and create a, well, we don't even need to put it in a variable. We'll say this root is equal to a new node built with this payload. All right, so if I have the empty tree currently, go ahead and set the root node equal to a new node based on this payload. else we have to add it to the right place in our tree. So we're going to ask some questions about our left and right child. So we're going to say if payload is less than this root, left child, get payload. We're going to say if it's less than or equal to that. If that's a true statement, if the root's left child, and we don't have this guy's in a private section right now, so we actually need to add functions to node to let us get our left and get our right child. So we'll go into node, just like we have an accessor for payload, we need to have accessors for left and right child. So we'll have a node pointer, get left child. And a node pointer, get right child. Go ahead and implement these inside of node CPP. Get left child will return this left child. Get right child will return this right child. So now we taught nodes how to tell us about their left or their right child. So we'll go back into our binary tree here. So now instead of left child, this is get left child, that function. So we'll ask our root to get us their left child. And then from that left child, we'll get the payload associated with that child. And we're asking, is the payload that we're trying to add to our link or to our binary tree, is it less than or equal to that? If it is, then we want to add this payload to the left. Else, add this payload to the right. All right, and how do we add stuff to the left or right? Well, we're going to have to build that ability in. We're going to have to teach nodes how to build add left, add right. Oh, I'm sorry, just add. So we're going to teach a node, just like a binary tree, is going to have an add function. We're going to teach a node to also have an add function. And what I want you to pay attention to as we're going through here is we're building this guy, this binary tree, in terms of nodes right now. But if we go back here, and this is something I want us to think about, this whole thing is a binary tree, correct? Is that guy a binary tree in and of itself? What do you think? Does that meet the requirements of a binary tree, just what I have highlighted there?
Yes, it does.
Okay. Is this guy a binary tree?
No, it's not.
Okay, tell me why.
Because the 9 is greater than the 0 and it's to the left of it where it should be to the right of it.
Actually, hold on. Is this not a legal binary tree the way we have right now? This isn't a legal binary tree that we have right now. We must have been kicking stuff around. Why did we put the 9 there? Well, here, let me just correct it. See the open less. Here, let's ask it that way. Is this a legal binary tree? Now we got a legal binary tree, right? So is it fair to say that a binary tree is a collection of binary trees? Are the left and right child actually binary trees? If this is a binary tree that has a left and a right child, is the left child a binary tree? And is the right child a binary tree? They really are. This guy's a binary tree whose root node is 1. This guy's a binary tree whose root node is 4. This guy's a binary tree whose root node is 2, so on and so forth. And actually all our numbers are messed up in here. This guy should go over here. This guy should go over here. I think maybe I was showing you n-ary trees or something. This is less than it. Well, here. Let's put a 0 here. That's fine. And this would be a 1. Now we have a legal binary tree. So the idea here is that a binary tree is actually a collection of binary trees where the left child and the right child are actually a binary tree in and of themselves. So if we come back in here and we say, what are we doing for a node? Well, a node holds a piece of information that is the payload. If I'm saying this guy is a binary tree, can a binary tree itself just hold the payload? Sure, it could hold that number 1. A binary tree can have a left child and can have a right child, both of those guys being a binary tree. So what I want to do here is we're going to take this information about a binary tree, about node rather, as of right now. And we're going to put this into our binary tree, where a binary tree itself has a payload, and then it has a left child, which is a binary tree, and it has a right child, which is a binary tree. So this guy no longer needs to include node. And we'll go ahead and take our getters here for our left child, right child, and our payload. We'll put those into binary tree as public methods. So now these guys don't return nodes, they actually return binary trees. So a binary tree holds a payload, which is its value, its root, if you will. And then it has a left and a right child potentially that are both binary trees. By doing this.
Question.
Go ahead.
So what's like, how do I word this? What is the benefit of doing this rather than just pointing it to certain nodes?
The difference is going to be what we were about to do in here is we were asking this question. If the root node's left child is payload is less than or is greater than payload, then we want to add it to the left. So what will we do? The left in that case is a node. We would then need to teach that node how to add a payload to itself. And that node is going to basically ask this exact same question, is it not? It's
Yeah, that makes sense.
Yep. So effectively, we're duplicating our code where we're seeing a whole lot of similarities between node and binary tree. Why should we treat them any differently? Does that kind of make sense?
Yeah, that makes sense. Thank you.
All right. So we're going to go ahead and actually now delete our nodes. We no longer need this dude because we're going to actually handle it all inside a binary tree. A binary tree is a tree of binary trees. It's a tree of trees. All right, so rather than us thinking about the root being a node, the root is just the payload for this binary tree. And then it has two binary trees potentially hanging off of it. All right, so we're going to go ahead and implement these guys for our binary tree. So now when a binary tree is first created, it's going to get created with a payload. We need to make sure we describe that. In here.
Question?
Yep.
So does that mean there's no way to have an empty binary tree in this way?
The way we're writing it right now, that's true, but we are going to add the ability for an empty binary tree.
Okay, thank you.
So back in here, in fact, I'm going to ask you how we can make it be an empty tree here in a few minutes. All right, so binary tree for this guy, instead of setting the root, we're going to set the payload to whatever payload was passed in. And then we're going to set this guy's left child equal to null. And this guy's right child equal to null. That's our setup for a binary tree that starts off with a value. Okay. Now, I'll go ahead and ask the question now since you brought it up. How could we add a second constructor that would allow us to build a binary tree that is empty, that currently has nothing in it? How might you modify our current setup? And I'll show you our HPPP here. This will be the easiest way to look at this, since this just gives us the highlight reel of what we're dealing with here. How can I create a second constructor binary tree that takes no parameters, and this guy creates an empty tree? What does it mean for a tree to be an empty tree? Like if you were walking through the yard and you saw a whole bunch of binary trees strewn about, which ones would you say are empty? The ones that don't have payloads, right? Well, how do we claim that something does not have a payload? We could set the payload to, I'll go ahead and write something and tell me what's wrong with it. Let's go that route. Did I set that guy to like a -1 and that means it's empty? Why is that a bad idea?
It's holding a -1.
That's a legal payload, is it not? So you could have a binary tree that has a -1 in it. I'm trying to use this -1 as a way of flagging for me that, oh, this is actually an empty binary tree because there's not actually a payload stored in there. Because I'm trying to make -1 stand as a non-payload. Alternatively, I can pick some gigantic number, right? I can say something like, something like that. Same reason why this is a problem, right? Now that we've disqualified that as being a payload. So how can we make this work so that we can actually have a tree that thinks it's empty? If we're saying that a tree that has no payload is the empty tree, how do we ask the question? Is this tree an empty tree, or is it something that actually has a payload? What can we modify in here to teach a binary tree how to know whether it's an empty or a filled tree.
You could add like a Boolean flag somewhere in the private section.
Yep. So we could do something like bool. Is it bool like that? Or is it bool like that? Bool like that. So we could say bool maybe is empty. Like that. And then in our implementation, I mean, we could default payload to something if we wanted to, just to give it an initial value. But we would say this is empty is equal to true. And in that case, we actually probably would not give it a default value. So if we're building a binary tree without a initial value, we would say that this tree is actually empty. If we're building it with an initial value, we would say is empty is false. It has a real value in it. Now, these two lines here, we might say that we probably don't want to duplicate those two lines, so maybe we could pull those things into another function, but it's just two lines, probably not the end of the world to do that. We actually can do this. I think this will let us do it. I think the syntax like this. We can call our parents constructor first, not our parents constructor. We can call an alternative constructor first, which initializes all these things. Then we can differentiate ourselves like this. We'll say initially create an empty tree, then make it not empty. So if we call this constructor where we pass it a payload, we'll go ahead and first build an empty tree. Then we'll make it a non-empty tree by changing the isEmpty flag to false and setting the payload to that value. That way we're not repeating these two lines in two places. This is probably better programming practice. Even though the other way would have worked fine if we just wanted to duplicate these two lines. All right, so we have two different ways of building binary trees. We can build an empty tree, or we can build a tree with something in it, which is built in terms of an empty tree and then a couple of little flipperoos. All right, and that's a official object-oriented term, flipperoo. I think, probably not. All right. Now we need to implement these guys. We're going to teach a binary tree how to get its payload, how to get its left child, how to get its right child. Return this payload. Return this left child. Return this right child. All right, so these are just getters for those private fields. I'm going to ask another question here in a second. How do we change the way we ask whether this binary tree is empty or not? How do we ask an instance of binary tree, are you empty? No longer asking if root is null, right?
Wouldn't you check to see if bool is true?
Yeah,
Like, is empty is true?
yep, we want to ask if it's empty, then we can put something here. We're not trying to add to one of the children. We have room right here. So we're going to say if this is empty. If this tree is empty, then what do we want to do? We're going to go ahead and set this payload equal to payload. And then set this is empty to false. Okay. Otherwise, if it's not empty, decide which child to add the value to. So we're asking if payload is less than this get left child get payload. Now, let me ask you something. Go back to this. Do I need a, let's just deal with get left child and get right child. Right now, we're only calling get left child and get right child inside of binary tree. So I'm inside the binary tree CPP file right now, and I'm saying, is the payload that was just passed in, is it less than this get left child get payload? Do I need an accessor method like get left child here? Did I actually need those guys if I only ever intend to call them inside of the binary tree class? What does private mean? We have a private section. What is a private field, or, well, yeah, in this case, field. Where are private fields accessible? We have three levels. We have public, private, and protected. C++, I think it's friend. Or is there a protected? No, there's protected. Isn't there a friend too? Maybe that's just been circumvented with protected now. So what's the difference between private and protected? Let's start, or a private and public rather. What's the difference between those two sections? Why do I have some stuff up here and other things down here?
Private stuff can only be accessed from within that class.
Okay, and that's the key here. And I'm going to actually add a little word to that. I think you meant the right thing, but private stuff can only be accessed from within the class named binary tree. It doesn't have to be the same binary tree. And what I mean by that is, if I go back to the code here, right now I have these extra accessor methods. These would be necessary if I wanted to access the left child or the right child from outside of the binary tree class. So I'm not going to delete these quite yet, because I think we're going to leave get payload in here, because it's reasonable that outside of the binary tree class, we might ask a binary tree what its payload is. That seems like a feature that might be helpful. But The structure of a binary tree, the left child, the right child, that kind of stuff, it might be reasonable for us to say nobody outside of binary tree needs to actually have access to that structure. So with that in mind, before I remove it, inside, I'm inside of the class binary tree. The current binary tree I'm dealing with is this. And this has a left child. Which has a payload. This is legal now because I'm no longer separating them between binary trees and nodes. I am inside of a class called binary tree, CPP here. So I can talk about this guy as well. I can talk about the payload that was just passed in here. And I can compare it to this guy's left child, which is another binary tree, and that guy's payload. I'm allowed to directly access this variable, and I'm allowed to directly access this guy's payload, even though payload is a private field. Because I'm still inside the class called binary tree, I have access to this other binary tree's payload. Okay, so private members are accessible anywhere inside of the class with that name, even if it's a different instance of that class that we're talking about. This is this particular instance of binary tree. So this dot payload is talking about the current instance of binary tree's payload. This dot left child dot payload is my left child, which is also a binary tree, his payload. And I have access to that private field here because I am still inside the file called binary tree CPP. All right, that makes some sense? So with that in mind, until we decide otherwise, I'm going to go ahead and remove those accessors or those getters. We no longer need getters for get left child and get right child because we don't presume right now that we're going to need to access those things externally to the binary tree implementation file. When we go over to main, for example, when we write our main program, our driver, it's entirely possible we might create a binary tree. We might ask that binary tree for its payload. And in that particular case, having that getter maybe still makes sense. But we're going to say that a binary tree is an abstract data structure, which means it's a structure for holding data, and it works the way it works. And all those details are hidden inside of it, right? This goes back to when we first talked about object-oriented programming. Our example of the object-oriented telephone versus the procedural telephone. The procedural telephone was that big pile of wires, whereas the object-oriented telephone looks like a telephone. We know those wires are all stuffed inside, but we don't actually have to have access to them. All right, so if and this also goes back to the midterm exam, where one of the things I tried to harp on, where a lot of people tried to reinvent the wheel. You know, I said, hey, you have a linked list that already knows how to do this crap. Now just use the linked list. If I'm using a binary tree, if we've already implemented that binary tree, we've already shoved all those wires into that binary tree and hid them from ourselves. And now I'm saying, look, we want to store some stuff and we want to keep it stored in a certain order. How do we do that? Well, maybe a binary tree is a tool that makes sense. So we won't necessarily need to directly access left child and right child. All we would say is add a value to this guy or find a value in this guy, search the binary tree for some value and give me the answer or -1 if it wasn't found, something like that, whatever maybe we treat it like an index of function, whatever that is. But we wouldn't necessarily be talking about those inner workings of that binary tree, like the left child and the right child. Those are details left under the hood. Okay, So I'll go ahead and remove them from here. And we'll also then not implement them over on this side. But we will still leave the getter for payload, as I think it's reasonable that we might want to ask a binary tree to give us their payload. All right, so now back into add, we're asking the question, if this tree is empty, go ahead and just put the payload you're trying to add right here and go ahead and flag this tree as no longer being empty. Otherwise, if the payload you're trying to add is less than or equal to this dude's left child payload. Now, what's wrong with this line? Let me just ask it that way. What does this line assume is the case that might not necessarily be the case?
This assumes that the binary tree has a left child.
Right. If we're dealing with a very early stage binary tree, we might have a tree that is not empty, right? Meaning that it already has a payload here, but he might not already have a left child. This might be the second value we're adding that happens to be going to the left. So we can't just do this arbitrarily. We need to only do this if he has a left child. All right. So if this left child, if that's a true statement, that means if left child is a thing, this dot left child points to something, it already has a value, as opposed to being null. So you can also write this as not equal to null if you prefer that syntax. I would say this is the more expressive version of this syntax, but it is somewhat redundant because null is a value of 0 or 1 because everything is done with numbers as opposed to like Java, where under the hood, Booleans are implemented as integers or maybe byte type, whatever, some integer type value. But we don't get to experience Booleans in Java through their numeric values, where in C++, if for some reason we really wanted to, I can't come up with a good reason, we can actually do math with Booleans because they are just numbers. All right, so there's more examples of things in C++ that you might not ever have a good reason for doing this, but you could do this if you really wanted to. So you will see in a lot of code examples, if somebody wants to ask if the left child in this case exists, they would just ask it like this. If this variable holds something, do something. All right, so if that guy holds something and the payload you're trying to add is less than that something, we want to go ahead and add it to the left. Now, we're only going to do this under what condition? If the value we're trying to add is less than our value. Because this question here says, which side should we go to? And I'm actually going to write it up here. If I'm in this else, I know that I don't have an empty list. So at the very least, if I'm right here, I know that this tree has a payload. And all I need is this tree's payload to ask the question about where this new payload we're going to put should be. So else, if this payload, if the payload we're trying to add is less than or equal to this dude's payload, if this is true, we need to add to the left. So then we can ask the question, if I already have a left child, we're going to do one thing. If I don't already have a left child, create a left child with this payload. So we'll come back to this if part here. So this else if says, if the payload I'm trying to add is less than or equal to this tree's payload, then the value is going to go to the left somewhere. If I already have a left child, we're going to do one thing. If I don't already have a left child, then I need to create my left child with this payload. I now have a place to put it. So I'll say this dot left child is equal to a new binary tree built with this payload. That will add it to my tree. If I already have a left child though, my left child already exists. That means I can't just put my payload in that left child. Presumably the left child's already taken. That parking spot's already being used. So I need to still add this to the left. So what line should I write here to add my payload to the left? This is what I referenced last class about the pseudo recursion thing. How do we add a value to a binary tree?
You call add on the binary tree.
Call add on the binary tree, and we're adding it on the left child's binary tree. So we'll say this left child add payload. So if I already have a left child, do I already have a left child? If so, go ahead and I'm going to rewrite this sentence a little bit. Ask the left child to add the value. Whatever that means, right? The left child might be able to set it to their left or their right child. Okay, or they might have to create they might pass the buck on to their left or their right child and tell them to add it. All right, so if I have a left child already, whose responsibility is it going to be to place this? It'll be that left child's. If I don't already have a left child, then I'll go ahead and create one with this payload. So I have now placed the value I'm being asked to place, and I'll place it in the left child. That's what I do if the binary tree rules say that my payload should go to the left. If the payload is less than or equal to this payload. Else, we need to add to the right. So we'll pretty much do the same questions in here. So we'll say if this right child, if the right child is a thing, what will we do? We'll say right child add payload. We'll just ask our right child to do the work. Otherwise, if we don't already have a right child, we'll say this right child is equal to a new binary tree built using this payload. All right, so to add something to a binary tree, what do? We first ask, is this the empty tree? If it is, just set the value here. This guy's probably only ever going to fire on the very first element of our binary tree when it's actually empty. We never actually create empty trees otherwise. This just allows the people to ask or to create an empty tree initially if they wanted to. So if it's empty, add it here, set is empty to false because it's no longer empty. Otherwise, if the payload we're trying to add should go to the left of this non-empty tree, and we already have a left child, ask that left child to add it. If we don't already have a left child, set our left child to this new binary tree with this payload. Otherwise, this is the else to this guy, the payload must be added to the right. If we already have a right child, ask the right child to add it. If we don't already have a right child, set the right child equal to a new binary tree around this payload. All right, this makes sense? Now, if we wanted to, for testing purposes, we could decide that we also want to, in our binary tree, maybe we want to also keep track of a count. Maybe we are just interested in how many elements are in our binary tree, for example. So that means when we create our empty binary tree, we would set count to 0. But when we create our non-empty binary tree, we would set count to 1. There's 1 element in our initial binary tree if we use the constructor that takes in a payload. Okay. That means that inside of add, whenever we add a value, we should increment our count. So we're adding a value here. We're actually not adding a value here. We're asking the child to add the value. So the child would be the one who actually increments the count. We are adding one here. Weird. This count plus. Did I not copy this? So we're the ones adding the child here, so we'll increment the count. We are not adding the child here. We're asking the right child to add it for us. So it would be their job to increment the count. We are adding it here, so it's our job to increment the count. So any way you cut it, we should now have the ability to keep track of the number of elements in our binary tree. Now, we go back here, we ask the question, my count is in the private section. Is it reasonable for us to be interested in the count external to the binary tree class? If I have my driver program and I've added 20 things to my binary tree, and then I ask, what's that binary tree's count from within driver? Is that a reasonable thing for us to ask? We might want to know how much crap is inside of the binary tree.
Yes.
Okay, so with that in mind, we probably then want to have a getter for that. Maybe get count. So we'll teach our binary tree how to return its private member count. We're inside binary tree here, so we have access to that private member, but we want to give somebody else public access to that, but read only. So that's why we make it private, but we give them read only access to it through this getter. Okay. So at this point, we should have a functional binary tree that does store stuff, and we should be able to put some stuff in it. We don't necessarily know yet if it's storing it in the correct way, but it should be storing it, we believe, in the correct way, and we should at least be able to look at our counter afterwards to make sure it's the right stuff. So let's go ahead and let's write a little test guy for this. I'm going to create a new file. We'll call this guy driver.cpp. We will include IO stream. We'll say using namespace std. Then we'll say int main, int argc, char pointer argv. We'll return a 0 at the bottom of this guy just because. I'll go ahead and include binary tree HPP. We'll create a binary tree here. Binary tree pointer BT is equal to new binary tree. And we'll go ahead and create our empty tree initially here. And then we'll say BT add a 5. To 13, 17, something like that. And then we'll do C out, BT get count. And that should give us 4 elements that are in that binary tree. Again, we haven't confirmed that we're adding them correctly, but assuming this all compiles and stuff, we should have a binary tree that started off as the empty tree because that's the constructor we used. And then we added 4 elements to that tree, which should get us a count of 4. We started off as a 0. Why did we only get a 3 out of that? We added the 5, we added the 2, we added the 13, we added the 17. This guy started off at 0. So when we added the 5, we incremented the count. When we added the 2, it should go to the left of the 5. So we're no longer empty. Is a 2 less than or equal to a 5? Yes, it is. We did not have a left child, so we asked our left child to, I'm sorry, we did have a left child in this question. We don't actually currently have one. So what did we do? We set our left child equal to a new binary tree with this payload. And then we set this, no. This is correct. So we created a new binary tree for our left child. This particular binary tree has a count of 1, this inside one, but we also incremented our count, which now should have gone from a, started off as a 0 right here. It should now be a 1. Right here. Then we added our next number, which whether it went to the right or the left, it should now be a 2. Oh, then we added our next number, which is now a 3. So 3 is the correct answer. What we probably want to do in our get count is to return count plus 1. That's the number of actual elements that are in there living at bucket 0 through the get count minus 1. So there's our 4. We go back into our code here for driver, and we instead build our initial tree with a starter value of 21. Now we should have a count of 5. Bro.
I have a question.
Sure.
Would it be possible to just, at the top of add, you just increment the count by 1? Because if you call add, it's for sure going up no matter what.
Yeah, I see what you're saying, because before I was saying we only want to increment the count if this particular tree's job it is to increment the count. But I think you're right. The reality is that whatever tree we're currently in, if we're adding a value to it, that this tree does get 1 larger, whether they're the one who is adding it or somebody else's responsibility for adding it. So what he's saying, which I think is correct, is take this guy, no matter what, our add function will make the count go up by 1, no matter what, for this particular tree. Our subtrees will have their own counts associated with them. So if I go back to our picture over here, this tree has a count of 1, 2, 3, 4, 5, 6, 7, 8. This tree here has a count of 1, 2, 3, 4. This tree here has a count of 1. This 2. This tree here has a count of 1. This tree here has a count of 3. This tree here has a count of 2, has a count of 1. So each subtree will have its own count relative to it being the root. But you're right, whenever we add something to this tree, the count for this tree will go up by 1, no matter whose job it was to add it. Yeah, and now our count is actually correct, so we don't add 1 to it. We just return the actual count. So there's the 5 in our case where we do create a non-empty tree initially. And then here's the 4 in the case where we do create an empty tree initially. All right, so now we have our tree presumably holding values the correct way. So what comes next? Now for the assignment, we're supposed to write visit in order, which if this worked right, we should get our values in the correct, in sorted order. So visit in order says visit to the left, visit yourself, visit to the right. So we're going to teach a binary tree how to, let's see, why don't we just have a tree just print out its payload. So we'll have it do void visit in order. And then we'll go and implement this guy. Oh, Ninja. All right, so visit in order says that we should visit our left child in order, if we have a left child, then visit ourselves, then visit our right child. And visiting for us right now means just printing it out. So if we have a left child. This left child visit in order. Then this then see out this payload. And if I want, I can just put a space here so it'll all be on one line. So I need to make sure that I include IO stream. And really visiting in order, we only want to do any of this if we're not empty. So if this is not empty, then we're going to say if we have a left child, visit it in order. Then visit ourselves. We know that we do have a payload since we're only in here if we're not empty. Then if we have a right child, visit that guy in order. So visiting a tree in order, we'll have it visit the left, if there is one, then visit ourselves, where we'll just output to the screen this particular guy's payload followed by a space. And then if there's a right child, visit that guy in order. So it's our left, then ourselves, and our right. That's in order.
So are the other two things, pre-order and post-order, as simple as like just moving those 3 lines around?
Absolutely.
Okay.
So now I should be able to say BT visit in order. We did make that guy public, right? I believe so. Visit in order is a public. So we can call it from here. So we'll go ahead and add the 5, the 2, the 13, the 17, the visit in order. We should get a 2, 5, 13, 17 out of this. Two, 5, 13, 17. So that should prove to us that we built our tree in the correct order. Go ahead and put this up on GitHub. We'll call this CSC300 spring 2021 binary tree. Make it public. Here, I'll just make this extra simple here. So I'll go ahead and do a VI push. Put all those lines in there. I'll run this. Build the push. Oh, because we didn't do a git add. Okay. Did I not actually create that because it failed the first time? Try to take a shortcut. Did it not? Must not have. Now it's up there. Refresh this. Copy that. So for your homework, which should not take very long, but you'll want to get your code up to date with this guy. Using our binary tree. So there's the starting point. If you want to look at mine, implement visit pre-order and visit post order. Submit a GitHub link and the self eval. All right, so as long as you followed what we did in class today, there's a decent chance this assignment won't take any more than like 5 minutes. If not, then make sure you study the video and figure out what we did in class today. All right, questions, comments, concerns, bribes?
Yeah, if my program already did that, do I have to hand anything in?
Well, resubmit your GitHub link if it already does it, just so I have something to grade.
Okay.
You don't need to change anything if it already accomplishes this.
Question.
Yep.
If we were able to accomplish in order correctly a different way, do we have to implement it with how you did the binary tree?
Well, you don't have to, as long as it's working. I mean, I'm fine with it. I would still probably, if you did your binary tree in terms of nodes, I would update it to do it in terms of a tree of trees. You're not going to lose points if you don't. I mean, it doesn't really matter to me. But you know, the goal of today was to look at this and realize that this abstract data structure is actually a collection of itself.
Yeah. Okay, that makes sense.
All right, anything else? All right, I'll see everybody on Tuesday, and I'll get the video uploaded and I'll get this put on Blackboard right now.
Dr. Whitman.